Assalamualaikum, and my name is Shamini Noor Shazana binti Abdul Khalid, and my ID matrix is 17 DIP 23F2059. So I'm going to start with my Enterprise Network PBE Task 1. I am from the questions. I am the network support engineer for Technova Solutions. Today, I explain how we identified and fixed and connectivity issue between our HQ and branch offices. The problem: our user reported two main issues. They could not access shared files between offices. They experienced slow response times and pinging internal servers. Essentially, the network was unstable and some advisors couldn't talk to each other at all. Network investigation. Look at our addressing table. I checked three case area, which is LANs. HQ is on the 192.168.1.0 network, and the branch is on 192.168.2.0. The one WAN, the two routers are connected via a serial link using 10.10.10.0 subnet. The gaps: I noticed the addressing table is missing subnet mask and default gateways for the cases and switches. This is a major reason why the end-to-the-end communication is failing. Troubleshooting steps. To fix this, I followed these steps. Verifications. I checked the physical cables and the serial link between HQ gap R1 and branch R2. Second is configuration. I assign a standard subnet mask like 255.255.255.0 to all devices. Gateway setup: I set the PC and switch gateways to their local router IP. For example, 192 and dot 168.1.1 for HQ. Routing: I ensured that both routers have a static route or a routing protocol so HQ knows how to find the branch network. Conclusion: after applying these settings, we ran a ping and trace routes test from PCA to PCB. The connections is now successful and stable. Our internal network is fully operational. Thank you.
Selamat sejahtera, nama saya Esther Shini Anakapa Surendra. Hari ini saya akan membentangkan task 2 iaitu mengenai cara dan langkah untuk menyelesaikan masalah kerangkaian atau troubleshooting. Untuk bahagian A, ada dua cara untuk cari masalah iaitu method. Yang pertama adalah cara atas ke bawah, top down. Kita perlu cek perisian dulu, contohnya kita tengok Google Chrome atau sharing folder boleh buka ke tak. Kalau aplikasi okey, baru kita cek kabel kat bawah. Yang kedua adalah cara bawah ke atas, bottom up. Ini terbalik. Kita kena cek barang fizikal dulu dan pastikan kabel tak putus dan lampu kad router menyala. Kalau semua barang fizikal okey, baru kita cek setting dalam komputer. Untuk bahagian B, mempunyai 7 langkah untuk menyelesaikan masalah SOP. Yang pertama adalah kita perlu cari kuncinya dan perlu tanya user apa yang tak kena, contohnya tak boleh buka internet. Yang kedua adalah kita perlu tahu sebab apa. Kita perlu buat teori sendiri, mungkin kabel longgar ataupun IP address salah. Yang ketiga adalah cek teori. Kita perlu uji teori kita, contohnya guna command ping untuk tengok ada sambungan ke tak. Yang keempat adalah kita perlu rancang cara untuk baiki. Kalau betul IP salah, kita plan macam mana nak tukar IP address itu dengan betul. Yang kelima adalah baiki. Kita perlu teruskan dengan buat kerja perbaikan sampai selesai. Yang keenam adalah double check. Kita test semua PC tu, pastikan betul-betul dah boleh masuk internet semula. Yang ketujuh adalah catat, iaitu rekod. Kita perlu tulis apa masalah tadi dan cara baiki sebagai rujukan masa depan. Itu sahaja daripada saya untuk task 2. Sekarang saya akan serahkan kepada intern untuk sambung task 3. Terima kasih.
Okay, section A software tools comparison. First, let's look at our software options. We have compared two industry standards. First one is Wireshark. This is a protocol analyzer. It captures and analyzes network packets in a real time, which helps us identify specific traffic issues or errors within the data flow. The second one is Packet Tracer simulation mode. Unlike Wireshark, Packet Tracer is a simulation tool. It allows us to model network behavior and visualize how packets move through a design topology to catch configurations error before deployment. The comparison Wireshark is for troubleshooting live, real-world networks, while Packet Tracer is primarily used for simulation, testing, and learning in a risk-free environment. Section B, Hardware Tools Comparison. Moving on to hardware, we use physical devices to diagnose the infrastructure. Cable tester, a fundamental tool used to verify if networked correctly. It detects broken wires or miswired sequence in the physical layer. Network analyzer, this is a more advanced device that monitors overall performance. It looks at traffic congestion and identifies broader system faults. The comparison, a cable tester is specialized for physical connection issues, while a network analyzer focuses on the overall health and efficiency of the network performance. Okay, section C, recommended tools for this project. Based on our specific scenario, we recommend the following two tools. First one is software tool, Packet Tracer. This is because of our network is currently in a simulated environment. Packet Tracer makes it easy to test various configurations without needing physical hardware. Okay, the second tool is the hardware tool, which is a cable tester. It is the most efficient way to quickly rule out the most common point of failure, a faulty physical connection or a damaged cable. Moving on to task 5, we will discuss the common symptoms we encounter in a failing network and the potential root causes behind these issues. Section A, 3 possible symptoms. On the left, we have identified 3 major symptoms that indicate a network problem. The first one is inaccessibility of shared files. Users report that they are unable to open or locate files on the shared server. Number 2, slow ping response. When pinging external servers, we notice high latency or lag. This suggests that while the connection exists, it is not performing at an optimal speed. And the last one is communication failure between HQ and. This is a critical symptom where devices at the headquarter office cannot talk to or see devices at the branch office, indicating a break in the link between locations. Section B, 2 possible causes. To address these symptoms, we have narrowed down the likely causes to 2 main categories. The first one is incorrect IP configuration. This is a logical layer issue. If a device has the wrong IP address, an incorrect subnet mask, or a faulty default gateway, it simply won't know how to route data properly. This leads to a total communication failure. The second one is faulty network connection. This is a physical or hardware level issue. This could be caused by damaged cables or misconfigured router interfaces. Any physical interruption here will be immediately drop the connectivity between our HQ and the branch.
Good morning, madam. So my name is Darshini. My card matrix is 17DIT24F1008. So today I'll be explaining about task 6, and then for the first thing I'll be explaining about systematic process of troubleshooting end-to-end IP connectivity. Specifically, we are looking at how to restore communication between PC A and PC B. In networking, as we all know, we don't just guess where the problem is, but we follow the logical by step methodology to isolate the failure point. So for the step one, we need to, it's based on the physical layer, that is like a foundation. So we always start at the bottom of the OSI model. Step one is like verifying the physical layer. It sounds simple, but we would be surprised how often this issue is just a loose cable or a faulty port. We check the NIC status lights on the both PCs and the link lights on our switches and routers. If there is no green light, there is no data following. So for the second thing, it is local configuration and the loopback, which is verify local IP configuration and then ping the loopback. So once we know the wires are good, we move the software side. In step 2, we run IP config on a PCA. We are looking for three things: a valid IP address, the correct subnet mask, and most importantly, the default gateway. Without a gateway, PCA can't talk to anything outside in its own local network. In step 3, we ping the loopback at 127.0.01. This is like a quick internal test. If this is fails, the computer's own TCP or IP stack is corrected. And the problem is with the PC's operating system, not the network. So for the fourth thing, we have ping the default, which is we test PCA can actually reach the exit of its own neighborhood or not. We ping the default gateway. If the ping is successful, we know the local switch and the connection to the first router are working perfectly. If it's failed, we are narrowed our search down to the local segment, the cable, the switch port, or the router interface. For the fifth step, we have of remote target, which is PCB. If the previous step passed but this one is failed, we know the issue lies somewhere in the cloud, the routing between networks. It could be a missing route in routing table or a firewall, or maybe in a access control list that is silently dropping out traffic. By following this 1 through 5 process, we have efficiently isolated a needle in a haystack. And for the part B, we have a logical plan. Let's look together at the two most powerful tools in a network engineer toolkit, which is ping and the tracer. While ping tell us if there is a problem, tracer tell us where is the problem. Like, let's look at the some outputs. Like, I have put the comments also. First, we use the ping command. We send small packet to PCB's IP. Let's say the IP is 192.168.2.10. If we say reply from, yeah, we are at the point. Like, but as a consultants, we care about the failures. If you see request timed out, it's a mystery. The packet might have reached the target, but a firewall is blocking the reply or the return path is broken. However, if we see the destination reachable, that's a major clue. It means like a router along the way literally has no idea, like how to get to the network. It's a routing table issue. So for the comment we put, that is already I put the comment, like what kind of comment that we can get, and then the interpretation also. So for the, if ping fails, which switch to trace it. Think of this like a GPS for our data. It's like every router or HOP hope the packet passes through. If we trace gets through HOP1 and HOP2, but start showing timeouts at like HOP3, we have just found out point of failure. We don't need to check the whole network. We just need to check the configuration of the third router. This saves us hours of troubleshooting times by pinpointing the exact break in the chain. So, and then yeah, that's all made. Yeah, thank you.
Task number 7, part 1, troubleshooting log. To fix the network, we follow three main steps. First, we realized the routers were mixing serial ports. We added HWIC to T modules, which allowed the serial cables to connect. Second, the links were showing red lights. We used the CLI to ensure the no shutdown command. This turned the interfaces green and active. Third, we fixed the communication gap. We configured static routers so that the HQ network and branch network could finally talk to each other. PCA can now successfully ping PCB. This is our final network diagram. On the left is the HQ side, and on the right is the branch side. The routers are connected via a serial link using interfaces CSE0 slash E slash 0. Each side has switch connecting the router to the local PC. All cables are now active and properly labeled with their interface names. Network baseline. Finally, why we need a network baseline. Think of a baseline as a health map of the network. When it is working perfectly, it records normal speed and error rates. By having this, we can troubleshoot much faster in the future. If the network slows down, we compare it to our normal baseline to find exactly what changed. It helps us move from just fixing things to actually managing the network health. Conclusion: the network is now stable, documented, and ready for long term use. Thank you.